Hello everyone. So today we are going to discuss another interesting problem on binary search. So the problem states that find the eighth magical number, right? So number is magical if it is divisible by B or C. Okay. So basically what we are given with is three numbers A, B and C, all integers, and we need to find the eighth magical number. So let us just understand this by one small example. So let us say that we are given B as 2 and C as 3, and let's just say that A is 8. So we need to find the eighth magical number such that that number is going to be divisible by B, that is 2, or C, that is 3 here. So the thing is, how we can solve this problem, right? So we need to find the eighth number which can be divisible by either 2 or 3, or it can be divisible by both. So let's just say that we are given a certain stream of these numbers. So we are need, like, let's just highlight all the multiples of 2 first. So I'm going to pick this yellow color for that. So 2 is one of the multiple of 2, right? Then we have 4, which is a multiple of 2. Then we have 6, that is the multiple of 2. Then we have 8, which is the multiple of 2. Then we have 10, which is a multiple of 2. Then we have 12, which is a multiple of 2. Right. So how many multiples have we encountered for 2 yet? Like this is 1, 2, 3, 4, 5, and 6 multiples, right? So then this is 14th, the 7th multiple of 2. Then this is 16, the 8th multiple of 2. Then this is 18, which is the ninth multiple of 2, and so on. Right. Now let us just consider multiples of 3 here. So I'm going to use blue color for that. So 3, this is a multiple of 3 itself, right? Then we have 6, which is a multiple of 3. For the time being, I'm going to leave it like this only. Then we are having 9, which is a multiple of 3. Then for 12, I'm going to leave it as it is. Then 15 is a multiple of 3. Then 18, I'm still going to leave it as is. And then we have 21, which is a multiple of 3. Right. So I've left 6, 12, and 18 just because these numbers are actually multiple of both 2 and 3. So I'm going to highlight them with a different color. So let's just say that I use this purple, or I could use a lighter shade of it. Yeah, this looks fine. So 16, then this is 12, and then there is 18, which is a multiple of both the numbers. So what problem is stating is we need to find eighth number. That is the eighth number, which is either multiple of 2 or 3, or it can be both. So if we start counting from here, right? So first we found this multiple, which is of 2, that is 2. So this is 1. Then this is another number which is a multiple of either 2 or 3, that is 3. So this is 2, you could say, like this is the second. Then 4 is again a multiple of 2, so we can consider it as the third one. Then 6, since it is a multiple of both, we consider it as fourth, right? Then we have 8, which is a multiple of 2 here, so we can consider it as the fifth. So what I am writing here is the eighth magical number, right? So this is the third magical number, that is 4 is the third magical number, which is actually divisible by either B or C or both, right? Similarly 8 is the fifth magical number, which is actually divisible by either B or C or both, right? Similarly 9 is the sixth magical number here because it is divisible by 3. Then 5 is the seventh magical number, and 12 is our eighth magical number, and so on, right? So ultimately our answer here is 8. right? So we found our eighth magical number, which is 12, which is either a multiple of 2 or 3, or it can be both. Okay, so this is what problem is asking for. So we will be given with these three values and we need to find this number. So one very brute force approach which comes into mind is like, why not just proceed finding all the multiples of 2 and 3, right? And then we maintain a count here which will always increment as soon as we encounter any of the multiple of either B or C, right? And as soon as our count is equal to 8, we return that number as the eighth magical number, right? So how the code is going to look like is, let's just say that our B is 2 and our C is 3, right? And our A is 8. Okay, 8. Okay. Now we need to find the eighth magical number. So currently here the series is extending up to, like it can go up to a lot of big range. So we need to define a certain range up to which we need to search for our eighth magical number. So what can we say, like can we observe something from here? The thing is that our eighth magical number, which is 8, is actually lying within a range, right? Like, for example, let's just say that we need to only find, if C was not given, and we need to only find the eighth, that is the eighth multiple of 2. So how are we going to find that? We multiply 2 by 8 and we get 16. So 16 is our 16. In that scenario, 16 would be our eighth magical number. If I am supposing, just let us assume that we need to find the eighth number which is divisible by 2, right? So it is very straightforward. We multiply the a by the given number, that is 2, and then we find the eighth number. Right. Similarly, for 3, we can say that suppose we need to find the eighth multiple, that is the eighth multiple of 3. So we just multiply 8 by 3 and we get the multiple, that is 24. Correct. Now, since we need to consider two numbers, right, B and C, we can say that these two numbers cannot be same. First of all, this is quite clear. These two numbers won't be same. So any one number, like from B and C, will be greater, right? Either it could be C or it could be B. So can I say that the range up to which I need to search for the eighth multiple is going to be lying till in the maximum of B or C multiplied by A, right? Because it's, if you would see here, like for example in this example, we are having A as 8 and C is 3. So if we multiply 8 by 3, it is going to be 24, right? It is going to be 24. So, and we can say that within this 24 range, the smaller number, that is B, is going to have more multiples than 3. Is, if that makes sense, like let us just, I'm just going to write it down here. So let's just say that eighth multiple of 3 is equal to 24. So 24 is the eighth multiple of 3. Now 2 is smaller than 3, right? So within this 24 range, the number of multiples of 2 is definitely going to be multiples of 2 within range of 24 is definitely going to be greater than the multiples of 3 within range 24, right? How can I say this? Because if we need to find the multiples of 2 within a range of 24, how can I do that? I just need to divide 24 by 2, which is 12. Since 24 is the 12th multiple of 2, I can say that there are 12 multiples of 2 lying within this range of 24, right? And there are at least 8 multiples of 3 which are actually lying within this range of 24, correct? So ultimately, if I'm considering both of these multiples, right, if I'm considering the numbers which are either multiple of 2 or 3 or both, then definitely I can be 100% sure that it is going to be lying within the range of maximum of b and c multiplied by 8. That is, here the maximum of b and c was 3, and multiplying 3 by the 8th, it is 24. So I can definitely ensure or be 100% sure that my eighth multiple is going to lie within the range of maximum of b c multiplied by a, right? So let me just write it down as an observation. This is our first observation from this uh, example. So by this we are actually defining our range, like up to what range I need to consider to find the eighth multiple of both of either b or c, because a magical number is divisible by b or c, or you can say that it is a multiple of either b or c, correct? So this is our very first observation from this example. So considering this observation, what we found is that the range in the linear search up to which I need to search for. So I can define my range, can say the range value is going to be lying within maximum of v c multiplying by 8, that is 8. Now once you define a range, now I'm going to search for that number, and it's quite clear, right, that our multiple cannot be negative, so we are going to start from 1 itself, because a can be 1 as well, and any of these number is 1, then ultimately our answer is going to be 1. Eighth magical number is going to be 1 itself, so that is why we are starting with 1. You can also consider the minimum value of these two to start with, because definitely, since had it been, let's say, had this number been 7 and this number been 4, so we won't be considering any multiples which are less than 4, because ultimately any multiple less than 4, like 0 is a multiple of, you can say 0 can be divided by any number, so but that is won't be considered in our answer. So we are going to start with, we can also start with the minimum of b and c in our situation, okay, but I am just taking it as 1 for now, okay, because it won't make any much difference, we will see that later here. So and now I need to search for the value in range from 1 to the range value. Okay, so within that range value, now I am maintaining a count. Currently, my count is 0. If my value is multiple of b, or my value is a multiple of c, then I can clearly increment by count, right? I can easily increment my count in that situation. And if my count is equal to a, then I can break from this loop, because once I have found my multiple or a value which is divisible by either b or c, and it is the eighth value or the eighth value, I can simply break, because I know there is no need for me to search further than that, and I can simply print that value. So for example, like we saw here, our eighth multiple in this example was 12, right? So here let's just see that if our linear approach is actually giving us the correct answer, and it will definitely give us a correct answer because it is totally based on this logic. right? That we keep on multiplying and incrementing the count as soon as we encounter any multiple of either B or C. And when we find that eighth or the eighth multiple, we just break from the loop and return that value. But what is the issue with this approach is that this is a linear approach. So ultimately, we are ending up having our time complexity to O of n, right? Or where n you can say, right? Where n you can say is what? It is the maximum of B or C multiplied by it, because this is the maximum range up to which we are searching for, right? So where n is this. But can we optimize this? Right, the question is that. So binary search now comes into picture. So how can we actually apply binary search in such a problem to actually get this answer is? Then we need to go into, like another observation from here. So what other thing can we observe here from is that since we found the eighth multiple, which is 12 here, right? Now up to 12, how many numbers are there which are actually multiples of 2, right? If I want to, if I'm asking like how many multiples of 2 are there up to 12, how can we find that? We just divide 12 by 2, which is 6, right? And what are those multiples actually? Those are 2, 4, 6, 8, 10, and 12, right? These are all the multiples of 2 up to 6, up to 12, right? These are 6 multiples of 2 up to 12. Now, similarly, how many multiples are there of 3? If I am to ask, right, how many multiples of there are up to 12? How many multiples are there of 3? So, there is 3, there is 6, there is 9, and there is 12. So, there are 4 multiples of 3 up to 12. And how did we found that? We just divided 12 by 3, that is 4. So, there are 4 multiples of 3, right? So, in this, right, if we consider now what is 8 is stating is that the count of multiples, right? The count of multiples of either 2 or 3 or both. This is one thing to observe is like this 8 is actually the count of multiples, which is from starting from this range 1 to 12. These are the count of multiples of either B or C. So how count is helping here is that let's just say that here there are 6 multiples of 2 up to 12, and up to 12 there are 4 multiples of 3. But if we decrement these common multiples, if you would see here, the common multiples are being considered twice. So if I decrement these common multiples here, right, if I reduce these common multiples, let's just say if I don't consider them, now can you observe something? See, there are 4 multiples of 2 and 4 multiples of 3, in which the common multiples of 2 and 3 are also being considered. Then ultimately it is giving us answer as 8, right? Ultimately it is giving our answer as total number of multiples, which is 8, right? So the 8, the number at which our total number of multiples is being equal to the A is actually our magical number. Correct. The number at which our total multiples for B and C is being equal to A, that is 8 here, is actually 12, right? So what we did here was we found for a number x, we find all multiples of B till x, which is equals to x by B. Then we find all multiples of C till x, which is x by C, right? This is what we did here. right? We found all the multiples of 2, we found all the multiples of 3, and then what we did? Since we considered all the multiples, then what we did? We were considering the common multiples of B and C twice. So we decremented those common multiples, right? We added these two and we decremented or find all the common multiples of 2 and 3, or you can say B and C till x, which is what? Which is x by LCM of B and C. Can I say this? Because what is 6 actually here? This is a common multiple of 2 and 3, but it is also the least common multiple of 2 and 3, right? And all the least common multiples of B and C, that is 2 and 3, are also going to be the common multiples of both the numbers. Like all the multiples of the LCM, that is 12 and 24, are also going to be the multiples of 2 and 3 itself. So instead of considering them twice, we just need to subtract these numbers. So like if I consider this value to be, let's say this is F, and this value to be G, and this value to be H. So ultimately for any number X, if my F plus G minus of H value is equal to A, then can I say that my X is the magical number we are looking for, or X is the Ath magical number we are looking for? I'm again going to repeat. So what we did was, like from observation, like for linear approach, we found 12 to be the number, or to be the Ath number, which is actually the multiple of 2 and 2 or 3 or both, and the eighth multiple basically of either 2 or 3 or both, right? It is actually the eighth multiple. So here we, our value of A was 8, so it is actually the eighth multiple of either 2 or 3, or considering both, right? So in linear approach, we incremented the count as soon as we encounter either of the multiples, and as soon as we found that multiple, we considered that number. Now, one observation from here is that since we know that 12 is our number, so let's just say that how many multiples are actually there up to 12 for 2, right? So we found that there are actually 6 multiples, that is just dividing 12 by 2, right? It is equivalent to finding what multiple is 12 of 2. 12 is the sixth multiple of 2, so there are ultimately 6 numbers up to 12 which are multiples of 2. Then similarly, we found all the multiples of 3 up to this 12, right, which are 6, 3, 9, and 12, right, which are 6, 3, 9, and 12. Now, one observation here is that we considered these common multiples twice. So, if I remove these common multiple ones, so I ended up with what? I ended up with a value 8, right? When I remove this 6 from here, right, let me just highlight it with red. When I remove this 6 and when I remove this 12, or when I actually removed the LCM multiples of both B and C ones from this count, so the remaining count of multiples, of numbers B and C, that is 2, 4, 8, 10, 3, 6, 9, and 12, right? This is equivalent to A, which is our eighth, or the eighth magical number here. So for any number x, let us say for any number x, if we are finding all the multiples of b, right, in that range, like if you're trying to find what is x, what multiple x is of b, so x is the x by b, or the fth multiple of, right, and similarly x is the gth multiple of c, that is, you can say g multiplied by c is equals to x, and here f multiplied by b is equals to x. right? And we subtract all the common multiples here. That was 6 and 12, and we subtract all the common multiples, considering them to be h. If this complete value comes out to be equal to a for any value x, then we can clearly say that x is the ath magical number which we were looking for. Right, and this is the very crux. This is the very uh, you know big observation to apply binary search in our scenario. So from this thing, we can state two things very clearly. What is our target? So target is basically to find the ath multiple, or you more specifically, I would say that to find a number x where the value of f plus g minus of h e is equal to it. This is our target. And to search for this number x, we need to define a certain search space or range. So the search space or the range for x is going to lie within what? From our earlier observation, we can say that this range can lie in maximum of this, that is maximum of b c multiplied by a. And this is how we can reduce our, or we can optimize our linear approach to binary search. Let us just see how we are going to go ahead with this thing. So for our example, b was 2, c was 3, and a was 8. Okay, so our range is going to start from left, which is going to be 2, let's just say, right? And for right, this is just the range, so I'm just considering it as left and right. So right is going to be minimum, or say maximum of b c multiplied by a. That is going to be 3 multiplied by 8, which is 24. Okay, now the how the binary search is going to take place, that we find the middle index or the mid value, and we consider the count of multiples here, or you can say the value of f plus g minus h. And if we can say if it is equal to, greater than, or less than, equal to, greater than, or less than a, right? So our left is 2, our right is what, 24. So our mid is going to be what, 24 plus 2 by 2, that is going to be 26 by 2, and that is going to be 13, right? So is 13, right? So is 13, now this mid is actually my x. Now I need to find all the multiples up to 13, all the multiples of 2 up to 13. So that is going to be 6. 6 plus, what are the multiples of 3 up to 13? That is going to be what? 3 fours are 12. So I am say 4. And what are the common multiples of both? That is LCM of both, that is 6. And what are the multiples of 6 up to this 13? That is 2. Right, here what we were doing, finding all the common multiples of B and C till 6, or we can say that find all multiples of LCM of B and C till X. Right, this is equivalent to that only. This above statement, these two statements means the same thing. Right. So now, once we are going to find all the multiples of LCM of B and C till X. So we can say that this is equal to H. So here the LCM of B, that is 2 and C, which was 3. LCM of B and C was 6. Right. So all the multiples of 6 up to 13 are, there are 2 total multiples. So if we try to find this value, what it is equal to, it is equal to 8. right? But we need to find the lower bound here. Although it is equal to it, but can we return this answer as is? No, we cannot, because this can be a value, but we need to consider the minimum possible value which can actually give us that answer. So to find the minimum value, in what direction we can go? We can decrement our right by mid minus 1, right? So we can decrement our right by mid minus 1 to find that minimum bound value. In that situation, we can consider this as an answer first, which is going to be 13. Okay. Now right is mid minus 1, that is right is 12. Left is again 2. And now our mid is what? 12 plus 2, 13, 14. And then our mid is 7. Right. What are the multiples of 2 till 7? Multiples of 2 till 7 are 3. 2 threes are 6. So there are only 3 multiples till 7. What are the multiples of 3 till 7? There are only 2 multiples of 3 till 7. And how many multiple common multiples, or how many multiples of 6 till 7? That is only 1, right? So this is giving us 4. So what can we say here now? Since this 4 is very less than a, we need to consider the values on the right. We need to increment our mid. So we increment our left by mid plus 1 in this situation. So now our left is going to be 8. Okay. And our right is going to remain the same, that is 12. Now 12 plus 8, that is 20, by 2, that is 10. Now multiples of 2 till 10, that is 5. Multiples of 3 in within this 10 range, that is going to be 3. And multiples of 6, that is 1. This is coming 7. Right, so again, this is less than a, so we increment left by mid plus 1. Okay, now left is going to be 11, right is going to be 12, mid is going to be what? 11 plus 12, that is 23, and 23 by 2 is coming out to be 12 approximately, if we consider the floor value of the division. So we are getting 12 here, right? 23 by 2, that is 12. Now multiples of 2 till 12 is going to be what? 6. Multiples of 3 to 12, that is 4. And the common multiples, that is the multiples of 6 within 12, is 2, which gave us 8. So now this is again can be our answer. So we increment our, or we can say that we consider our next, replace our answer by this newly found lower bound answer, that is 12, right? But again, there must be some terminating condition up to which we can search in the binary search, right? So our terminating condition is that as soon as my left is going to be greater than right, I can terminate at that situation. So still, again, since we are finding this, we will again decrement my right to find the lower bound if it exists by 1, right? So if I decrement my right by mid minus 1, so my right is going to be what? 11. My left is again going to be 11, that is 22, and my mid is going to be 11. So now my answer coming out to be for this situation is what? How many multiples till 11? That is going to be 5. How many multiples of 3 till 11? That is going to be 3. And how many common multiples? That is 6. How many multiples of 6 till 11? That is going to be 1. Sorry, 1. So this is again coming 7. So this is 7, which is less than a. So we need to go right and search. So we are going to increment left by mid plus 1. And as soon as we do this, right, as soon as we do this, what is going to happen? My left is going to be 12 and my right is going to be 11. This is the breaking condition, and we can simply break here, and our answer which we found was stored was 12. So we can simply return this answer with binary search. So this is how binary search is coming into picture and helping us optimize our approach over the linear way. In linear search, we are actually iterating through the complete range and checking for all for whether this is whether a number was multiple of 2 and 3, incrementing its count, and as soon as our breaking condition was as soon as my count was being equal to this a, I break at that situation, right? But the issue was that this range can exceed a lot, so we were increasing our time complexity to n. But with this few observations, right? Like considering the multiples of the b till that range, till that number for a number x, and the multiples of both the numbers and the common multiples, right, of b and c, that is the LCM. I was able to find that I need to search for only a number x, right, for which my this value f plus g minus h, that is the multiples of b, multiples of c, adding multiples of c, subtracting the common multiples, this value is actually equal to it. And as soon as I found that for any number x in a given range, I can simply return my answer, right? And conditioning here is that if that value, if f plus g minus h, this value is being less than the number or the ath multiple or the ath magical number which I need to find, if it is less than that, right, if this value is less than that, what I did, I incremented, or I said that okay, I need to search on the right hand side for that thing, and if it is was being greater or equal to than that number, that is it. So I said that okay, I need to find the lower bound, or I need to search for the on the left hand side, so that for that value, so that my multiples are actually coming equal to a. So this is how binary search comes into picture. So let us just see how the code is going to work here for the binary search approach. So most of the things are going to remain same. I'm just commenting this linear approach, or let me just remove it. First things first is that we need to find the LCM. Like here, what we are doing is that we consider the LCM of B and C. So one formula to find the LCM, if right, for any number b and c, the formula is HCF of b and c multiplied by LCM of b and c. Okay, both numbers multiplied, b and c multiplied, is equals to HCF of b and c multiplied by LCM of b and c. This is the formula. So we can find the HCF by this formula, right? Like if you know modulo how to use that, this is a recursive function which I'm going to utilize here. So let's just say this is num1 and num2. So if any of the numbers is eventually 0, I can simply say that the other number is going to be the highest common factor here for that number. And similarly, if my n2 is equals to 0, then I can simply return n1 in that situation. Else, I will find recursively what 2 percentile by n1 and n5, and that is it. So this function recursively is going to find my HCF and going to return me that. So by dividing the HCF of B and C, or by dividing B multiplied by C by its HCF, I can simply find the LCM of B and C. Okay, so this is sorted. Now our left is going to start from 1, or you can say the minimum of B and C, right? And my right for the binary search is going to be starting from B and C multiplied by maximum, right? So till the time my left is less than equal to my right, right, which we considered here. Yeah. So here what we did, we considered left till the time my left was being less than or equal to right. Here it was equal to. We considered our answer, or we continued in this loop. Now this is going to be our x basic. So that is left plus right by 2. Okay. Now I need to find all the multiples, multiples of 2 till x, right? So that is going to be x by 2. Multiples of, you can say b and you can say c till x That is going to be what? This is B, and this is what? C, right? And then the multiples, common multiples, multiples of B, C, which is going to be what? X divided by LCM of B and C. Can I say this right? So let me just pre-calculate this value because it is very inconvenient to again and again calculate this LCM, right? So I'm just going to do it this once here. LCM B and C is going to be what? It is going to be B multiplied by C divided by HCF of B and C, right? This is going to be in a line with this formula itself. Okay. So now when I know my LCM, so I just need to divide this by that for that. Okay. So ultimate total count is going to be what? This is the total count of multiples of either B or C or both. Is what? Multiples of B till X plus multiples of C till X minus common multiples of B and C. And now I'm comparing if this total count is equals to my A. In that situation, I can store my answer. That is the lower bound answer, right? Or we can combine two cases here. So if it is equal to, we were finding the lower bound, or if it is greater than A, then again we proceed in the lower area. So we can simply say if it is greater than equal to, we update our answer in all those situations. So answer is going to be what? It is going to be X, and my right is going to be mid, or you can say X minus 1. So X here is basically my mid here only, okay? And else my left is going to be X, that is mid plus 1. And this is pretty much it. Okay, this is going to help me find all the values, and then just need to print the value of my answer. All right. So this is how this thing is going to work. I can just move this and let's just see what answer does it give for. Okay, it gives us this error unsupported type. We put unsupported types HCF N1 and N2. Okay, we didn't return it from here. That's my mistake. We need to return the value which we found, right? So once we return that value, only then we can divide it. Now let's see. Yeah, so it gave us 12, right? Similarly, if you need to find for any number, you can actually do this. I'm just considering one example, and using this binary search, we were actually able to find this thing. So major logic lies between the count of multiples of B, count of multiples of C, subtracting the common multiples which were considered twice by adding these two, subtracting them, and then considering that if for this number X, this total count is actually being equal to A or not. And if it is was greater than or equal to A, we consider the lower bound in that situation. We considered towards the left hand side, we moved in the search space towards the left hand side. Else it was if it was lesser, then we moved in search space towards the right hand side. Because then we need to increment our range or our value to search for that particular range. So by applying binary search now here, we optimized our time complexity by log n, right? So now our time complexity here is log of n, where n is what? N is going to be the search space, which is maximum of B or C multiplied. Okay, this is how we optimized our time complexity or space complexity. In both situations is going to be 1 itself, because we are not taking any extra space. We are just considering over a range and storing most of the values in the variable itself. So space complexity is going to be constant. So that is all from this video. I hope you learned something from this. And if you have any kind of doubts in this question or a doubt in my approach of things, do let me know in the comments, and let me know how can I further improve my content sharing and like my thought process in these videos. So thank you for watching and have a great day.